634. What we want to do in this series of lectures over the next 2 weeks is talk a little bit about mating system design. What we're going to start out with is talking about different mating types and then move into different systems of mating and how and why we actually use those different systems and something about the strengths and weaknesses of those. The first of the systems we want to discuss is actually random mating, and that's a mating system in which mates are chosen at random. So if you want to put this on an applied standpoint or from an application perspective, you're going to have a group of bulls a bull battery that you would like to use in your herd, and you just put those bulls out with all your cows and who gets bred to who and what the offspring or the parentage of all of the offspring is kind of at random, just dependent upon which bull tries to breed more cows or which bull tends to be more fertile. You tend to get different numbers of offspring per bull with a random mating system. Whereas random mating doesn't require much knowledge of animal performance, the assortative mating systems require considerably more knowledge, because we want to take one of two approaches, and that's either positive assortative mating, where we're pairing males and females based on their performance, and that performance is rather similar or dissimilar, or negative assortative mating, where we're actually looking at dissimilar individuals. And the issue with assortative mating is that it's more difficult than random, so we need some idea of performance, genetic predictions, or some other criterion where animals are ranked. Now, you can use both types simultaneously in a herd depending upon what your selection goals are. So let's talk a little bit more about positive assortative mating. And remember, that's when we're mating animals that perform very similarly for the traits we're interested in improving. We're mating like performing to like performing. And so to give you some examples of that, you might mate, if we're looking to produce progeny that are extremely tall, we might mate the tallest bull or the tallest cow. Or if you're looking to improve or increase the height of your horses, the same type of thing, the tallest to the tallest, the best to the best. Or you might say something like, we're going to take the bull with the highest yearling weight EPD and mate it to that proportion of cows in my herd with the highest yearling weight APD. And what you're really trying to do is find or breed and produce the outliers, essentially animals that are very extreme using this mating system. And what this tends to do is increase your genetic and phenotypic variation in the population. So, I kind of use the term, this type of system is used by those trying to hit a home run and find that one very extreme individual for the trait they are interested in improving. Now, from a genetic improvement standpoint, that might be a good idea, but from a commercial standpoint, where you're trying to produce a very uniform group of progeny to sell, that may not be the best approach. So looking at this graphically and comparing positive assortative mating with a population where you've actually implemented some random mating system, and this is like a multi-sire breeding pasture. It's essentially which cow gets bred by which bull is random to a certain degree. And if you look at this, random mated population is shown in the dotted line, and I borrowed this from Dr. Borden's textbook, Figure 16.1. The population undergoing positive assortative mating actually starts to get a wider bell curve. That is, we're increasing the variability in that herd. Now with negative assortative mating, we're doing just the opposite. We're mating opposite extremes of individuals trying to produce some intermediate optimum. So we're taking the tallest animals and trying to moderate in their progeny height, so we mate those to the shortest females, so tallest males, shortest females, or vice versa. In the same way with EPD. You may have some cattle in your herd that have a very high birth weight EPD and some calving issues, and so you mate those to other individuals that have a very low birth weight EPD, trying to moderate that in the progeny. And so this actually tends to decrease variation, but it's not a good strategy for speeding the rate of genetic change. However, it is a good if your goal is to produce some intermediate optimum. And so this is the type of mating strategy we might use. Another term that this has been called is corrective mating. So if over time your cattle have gotten too big and essentially they require more feed than your ranch is capable of producing, or they're capable of consuming on a foraging basis, we might want to correct that in the next generation. So we want to moderate cow size, so we'll breed them to bulls that have the genetics to produce females that are smaller at mature size. So we're trying to correct in the progeny the faults of one or both of the parents. And if we look at this graphically, okay, again using the randomly mated population as our basis, we see that bell curve, or that distribution of progeny in our herd, start to shrink. That is, the bell curve gets more narrow but taller, meaning more animals are clustered around the mean. Negative assortative matings are also a good example of a phenomenon we call complementarity. And the easy way to remember this is we're really trying to take advantage of complementary attributes in the male, or the sire, and the dam of the next generation of individuals within our herd or our flock. So it's a corrective mating, and it's a good example of complementarity. So this first three sets of mating types, for instance, that we've covered, the first one is random mating, and we really, to implement that type of mating strategy, do not need to know much about individual animal performance. The assortative mating systems are more based on performance, where you need to know, are these individuals extreme within my herd for the traits I'm interested in improving, or are they moderate? And that helps you to implement one of the two types of mating systems. Now, within a herd, as I mentioned earlier, you can apply both types of assortative mating systems depending upon what your goals are. Now, there's actually another class of mating strategies that we'll talk about here in the next slide. Strategies that are based on pedigree relationship, that is, inbreeding and outbreeding. And we're going to talk really briefly about inbreeding because we want to spend most of our time on outbreeding and then eventually migrate to different crossbreeding systems. So let's talk a little bit about inbreeding as the first of our mating strategy based on pedigree relationship. Inbreeding is the mating of relatives. It's just pretty much as simple as that. So if we look at a sire and dam, trace their pedigrees back, if there's an individual that shows up in both of their pedigrees, no matter how far back, the offspring from the mating of those two individuals is going to be inbred. Now, inbreeding ranges from 0 to 1 and represents a proportion of genes in those individuals, or a proportion of loci where that individual has identical copies of a gene from a single ancestor that has passed genes on to both the sire and the dam. Now, we're not going to say a whole lot about this because it's primarily a tool for seed stock breeders, and it does some very good things for the seed stock breeder, but from the commercial standpoint, it doesn't help us a lot from a production perspective. So with that, let's go on to what this actually does for us. So let's talk a little bit about the effects of inbreeding. And there's several, both good and bad, that result from inbreeding. And again, I just want to review these because even though this is used primarily in the seed stock industry, I think you need to have a good background and understanding what inbreeding does, especially if you manage a commercial operation relative to genetic improvement and a few effects that can result from inbreeding. The first thing that it does is increase homozygosity. So if we look at the bovine genome and we have a particular locus, inbred animals tend to have a higher proportion of those loci where they are homozygous. And what's happening is that common ancestor, that animal that makes the sire and the dam related somewhere back in the pedigree, can pass genes on to both the parents, and then the same gene on to both the parents, and then those parents pass that gene onto the offspring, so it ends up being homozygous. Now, one of the benefits of that is you tend to get greater prepotency. That is, inbred individuals tend to produce sperm and egg cells that are more similar than animals that are not inbred. And so from a applied standpoint or a slang, those inbred progeny tend to stamp, if you will, their progeny. That is, they're tend to be more genetically uniform, and perform more similarly, assuming the dams are equal, of course. One of the other things that happens, it's one of the negatives associated with inbreeding, is the expression of deleterious recessives. Any of those of you who have been involved with breeding Angus cattle in the U.S. over the last 20 years or the last 10 years, it's really become prevalent, would know about the curly calf syndrome, and that is a single gene defect that became apparent. We didn't see it until we started mating related individuals from one line of Angus, that is, individuals that had a common male back in their pedigrees where we think this mutation originated. So we started seeing calves that had the curly calf syndrome. Now, that's on a one locus example, but related to that, we also get overall inbreeding depression. And inbreeding depression is a reduction in the performance of individuals because they're inbred, and that's typically with reduced survival rates and reduced fertility rates. Inbreeding by increasing homozygosity appears to decrease levels of fertility in those inbred animals. So let's talk a little bit about the opposite of inbreeding, and that is outbreeding. And what that is the mating of unrelated individuals. Now, from a general standpoint, we typically think about breeding as analogous to crossbreeding. But within a breed where we have different lines, we can look at crossing those lines, and you might consider that a form of outbreeding as well. And like I said, it most commonly refers to crossbreeding or line crossing, and that would be crossing those different lines within a breed. Now, the effects of outbreeding are several, and it increases heterozygosity. So let's think about this. If we're talking about inbreeding and we're saying outbreeding is the opposite, inbreeding increases homozygosity, outbreeding increases heterozygosity, and it also masks the expression of the deleterious recessive alleles with major effects. So when we discussed inbreeding, I talked about curly calf. We probably never would have found that if the Angus animals that were carriers of that disease had been mated to animals of other breeds and the progeny harvested. But when we started to inbreed within Angus, we got the expression of curly calf. In a crossbreeding situation where you're mating unrelated individuals, you would not see the expression of that deleterious recessive allele. And the main reason we talk about outbreeding is for hybrid vigor. And we'll talk a little bit about hybrid vigor more here in a few slides, but it's the primary reason we implement crossbreeding systems. So what I've done here is borrow a table from Dr. Rick Borden's textbook, Understanding Animal Breeding. And what this illustrates is the concept of hybrid vigor and how it increases when the sire and dam come from increasingly unrelated populations. Now remember, hybrid vigor tends to increase as we increase the proportion of animals that or proportion of loci in animals where they are heterozygous. So if we look at parents differing at 2 of 6 loci in the first part of the table, we see that their offspring get a gene combination value of 6, and that would be analogous to an increase in performance due to hybrid vigor. If we look at parents in the second sequence where they differ at 4 of the 6 loci, we get more gene combination value or hybrid vigor. And then if the parents differ at all 6 loci, so think of this as mating Angus to Brahman cattle, completely different frequencies from most loci in the individuals, we get an even greater gene combination value or amount of hybrid vigor. Now remember, back to some of our original lectures, our phenotype, or what we see, is actually a function of genetics and environment. And then we can further split out genetics into the breeding value, the component that's passed on, or half of that is passed on to the next generation, and then gene combination value, which represents the way alleles are combined in a particular individual. Okay, so there's some reasons to outbreed. Some of these are to cover the existence of the deleterious recessive alleles. As I indicated earlier, those alleles tend not to be expressed in the cases where you are using an outbreeding program. It adds hybrid vigor, and it takes advantage of breed complementarity. That is, taking the strengths of different breeds and combining them into a new crossbred individual or composite so that they leverage those strengths of the parental breeds to actually perform better in the environment for which they are designed. Now, with all of that said, outbreeding is practiced primarily by commercial producers. That's where we see most of that going on, except in the cases where we have composite breed formation, such as with Brangus, for instance, where we have complementary attributes combined from Angus and from Brahman into a new breed, essentially. Let's talk a little bit more about hybrid vigor. Hybrid vigor is an increase in performance of the cross or the first generation over that of the average of the parental line. So I want you to think about this from the standpoint of two different breeds. We're going to take two breeds of animals, whether they're sheep or hogs or beef cattle. We're going to cross those and measure performance in that first cross, or the F1 generation. So the P with a bar over it and the F1 is the average performance of that first cross generation. The difference between it and the average of the parent lines is hybrid vigor. And so what I want to do is illustrate this graphically in the next slide. But essentially, if you remember, breeding value, half of that is passed on from each parent to the progeny. What hybrid vigor is the increase in performance over what we expect due to breeding value. And this is due to heterozygosity and gene combination value. They actually do better than we expect. So let's talk a little bit about hybrid vigor and show what I just discussed on the previous slide in graphical form. In A, we have two parental lines, that is the P1 and the P2. And we average those parental lines to give us the double bar P with the subscript P. And we take the difference of that from the average of the first cross animals, or the offspring of the mating of those two parental breeds or lines, and we see a difference in performance over what we'd expect. What we expect is that P double bar in A, that's where we, based on breeding value, animals' parents pass on half their genetics. Now, if we go down to another option, you will see an example in B where we wouldn't recommend crossbreeding because the amount of hybrid vigor does not exceed one of the best parent lines. And the best example I can give of this in the industries, livestock industries, is our U.S. dairy industry. Most of our cattle are Holsteins because even if you crossbreed, you'll get hybrid vigor, but that crossbred animal won't exceed the performance of the Holstein cattle, and therefore there's really no reason to outbreed or try to take advantage of hybrid vigor for milk production. Now, for fertility traits, where we tend to see a lot of increase in performance, that would be a different story. So another way that we can express heterosis or hybrid vigor is as a percentage. And you'll see this typically or in a lot of the published literature rather than actual pound units, because the units relative to pounds or units of the trait depend upon the two breeds you've chosen, and this helps us just get a general feel for the overall increase across different mating systems, crossbreeding systems, across various crosses of particular breeds for that matter. So to express as a percentage, all we do is divide that value from the previous slide by the average of the parental lines and multiply it by 100. So we're going to take the previous slide where we express things in a percentage and look at the various levels of heterosis for traits in beef cattle. And this is a table from a bulletin that I will post on RamCT relative to crossbreeding in Western range environments. And immediately as you look at that individual heterosis percentage column, you'll see the biggest areas where we see performance increase above the average of the parents is in puberty. And that is especially for the percentage of females reaching puberty by 15 months of age. Heterosis in general tends to benefit fertility and survivability traits the most across various breed crosses. So what I'm saying is, no matter whether you mate Angus to Brahman or Hereford to Angus, we see across all those various trait combinations an increase in heterosis, most affecting fertility and survivability traits. You'll also notice that we get an increase in birth weight and weaning weight of about 4 and 5% respectively. So that says our calves wean about 5% heavier than what we would expect given the averages of the parents. So if we had an Angus line that weaned 500-pound calves and a Hereford line that weaned 475-pound calves, we would expect the average of the progeny to be the average of 500 and 475 pounds. That is, 487.5 pounds on average should be the weaning weight for a big group of those crosses. However, with 5% heterosis, we get an increase in weaning weight of just over 24 pounds. So really, in the end, those calves, based on this chart, would wean about 512 pounds, greater than either of the parent breeds. That's individual heterosis. Also notice that when we start to factor in cow longevity or lifetime productivity, that is really where we start to see the increase in performance. And I'll put this in a dollar value later on, but I'm specifically referring to the bottom right hand corner of the total of the picture, or in the total heterosis percentage. So we increase cow longevity of a first cross cow. So the first, if you cross Angus and Hereford, you get a black baldy female. We expect on average those females to last about 38% longer in our herds. So let me make a few comments on this idea of individual maternal and paternal heterosis. And notice in the previous slide we didn't see paternal, but I'll say a few words about that. So individual heterosis, is the hybrid vigor, the increase in performance in a particular trait in a group of F1 or first cross individuals that is a result of those animals being crossbred or having a large gene combination value or high degree of heterosis. Whereas maternal hybrid vigor influences the mothering ability of the female. So because she is crossbred, she produces a heavier calf. So in the mother, its gene combination value and high levels of heterozygosity give us an increase in performance of her offspring because of the care or the milk she provides for those offspring. And then the third, which we normally don't think a lot about in beef cattle or most of our livestock species, is paternal heterosis. There is some evidence that in beef cattle, crossbred bulls have the ability to service and produce pregnancies in greater numbers of cows than purebred bulls. In sheep, we see some of the same idea, and in pigs as well, where we get in sheep a higher incidence of twins and triplets, and in hogs we get a higher number of piglets produced at an individual farrowing. But we don't deal with this a lot, and we don't try to evaluate it very much in our livestock species, other than that instance. Incidences where we can actually lose hybrid vigor. So remember, up until now we've been talking about the heterosis or the hybrid vigor in that first cross offspring and when they become parents relative to their maternal heterosis. And we call that F1 hybrid vigor. It's the maximal amount we can get, and we get that in the first cross. However, in subsequent generations, so if we cross F1 animals with F1 animals, we lose a portion of that hybrid vigor. So from that point on, we call it retained hybrid vigor. So how much hybrid vigor is retained after that initial cross? So when we mate F1s back to F1s or F1s back to one of the parental breeds. And we call this the retained hybrid vigor, the hybrid vigor remaining in later generations of hybrids. And we only lose heterosis provided we don't inbreed in that first cross. And we commonly express this as a proportion of first cross heterosis as well. And in a subsequent slide I'll talk a little bit about how we calculate that. So let's talk a little bit more about percent retained hybrid vigor. Now I've shown the equation that we use to calculate how much hybrid vigor is actually left in offspring once we start to breed those back to animals of similar breed composition. And I don't panic because I want to explain everything. Okay, so in this calculation, we're going to take 1 minus some things that are added together. That's what the sigma is. It's summation. And that's a summation of the percentage of a particular breed in the sire times the percentage of that breed in the dam, where n represents the number of breeds in the cross and the number of things we're going to sum. So let's take a really simple example and say we have purchased some Sim Angus bulls, half Simmental, half Angus, and are going to mate those back to Angus females. Okay, so we know we're going to lose some F1 first cross heterosis because the bulls contain Angus and the females contain Angus as a breed. So the question is, how much of that are we going to keep? Not how much we're going to lose, how much we're going to keep. So if we use this example to actually illustrate how we calculate this, the calculation says the first term in brackets, the 0.5 times 0, says the proportion of Simmental in the bulls is 50%, but there's none in the females. Okay, so that's the first thing, first term, the product of the breed proportions in the sire and the dam, plus the second term, which represents Angus. There's 50% Angus in the bulls, and the Angus females are 100%. So if we look at that and do the math, we have 1 minus 0.5 times 0 plus 0.5 times 1. So that simplifies into 0.5 or 50%. 1 minus 0.5 is 0.5 times 100. We're going to keep 50% of that first cross heterosis in the offspring resulting from this mating. So some of you asking, all right, who cares? Why is this important? Well, if you look at this relative to a beef operation, there's research out of Montana State that shows, on average, a first crossbred cow returns $70 more per year than a straight-bred cow. So remember, that's above the average of the two parental breeds. Now let's move that to a 4-breed composite where there's a quarter of each breed. Those retain 75% of their F1 hybrid vigor. So what does that mean as far as profitability? Well, if you do the math, the change in return per cow per year is $52.50 increased return from a 4-breed composite per year over the average of the parental breeds. 75% retained heterosis, $70 increase in net returns per year per cow in an F1 female first cross. Multiply those together and we get $52.50. Now if you take that by the average cow lifespan, let's say it's 6 years, per lifetime we're getting $315 per head more profit from a crossbred cow, in this case a 4-breed composite, than we would the average of the parental purebred cows. Now this uses some older economic data and our prices have gone way up since then, but so we expect this to actually even be greater now as compared to when the research was completed. So that brings us to crossbreeding systems, which will be the topic of our next lecture series on mating systems.